That was too early. Good morning. Uh, I will start this with an introduction that has two parts. One is will be fun. The other one is a bit more technical. But what is my main aim on these lectures? So the idea is to take you to quantum anomalies and how they have now emerged in condensed matter, in recent condensed matter. So the objective is already to establish a link between two worlds, which is high and low energy. Then, for that, most of those quantum anomalies are really lying on the chiral anomaly. And this chiral anomaly that I will explain you about has two contributions. One comes from gauge fields, and the other one comes from gravity. I will explain you how anomalies give rise to anomalous transport phenomena, so the phenomena that normally they wouldn't exist, and because of these anomalies they do. And here is where thermal will arise. This is a lot of fun. This part will be quite at the end. I'm saying that because the title is Thermal Transport. I don't know what, but I will reorder it during the lectures so that you will have all the tools, at least to understand the concepts of what I'm going to talk about. This chiral anomaly comes from chiral fermions. So I will devote some time today to explain to you what a chiral fermion is, so that everything will be clear from the beginning and then we can proceed faster. So now, all that relies in quantum field theory, right? Sorry. Okay. So now start the fun part. Why quantum field theory? And there are many answers to this, but my main answers are: it is easy. Don't smile, I am seeing you. It is easy because there are some few technical points that you have to learn at the beginning. And then once you learn them, you acquire this technique, then everything is there and it's really easy. So it pays. Maybe if older people don't, are too old, but younger, go there because it pays. It is worthwhile, energetically favorable. Can you see the blackboard from the back? Good. And understand my handwriting? Okay. Okay. It is. So it's easy. It contains everything, almost all physics. And most important, it is a lot of fun. Okay, so let's start now. I'll start by reminding you, well, since I will need some tools to go through this, I'll remind you things that you have seen in the BA, but you maybe you didn't notice or you didn't think they were important. So I'll follow the Landau series, not for any special reason. If you don't like Landau, that's all right. But what I mean is that I'll tell you what do I need that you remember from classical mechanics, field theory, blah, 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 okay? This also will allow me to show this point of it contains everything. Because at the end, of course, I will throw some arrows that go from quantum field theory to everywhere else, almost. The almost, of course, is hydro or more phenomenological, the science that is difficult to, but even those, never mind. So, what did we learn? Lambda 1, classical mechanics. Next. What does it deal with? It deals with point particles, curious things, but it doesn't matter. We swallow that when you were young. With the mass, which is even more weird, having no, but anyway. It is important that it is massive point particles. Of course, point means these particles are, well, I don't like this point, but anyway, particles. I'll tell you why I don't like this point later. But they move at a speed much less than v, than c, and nothing else. So what is our object of desire? Meaning, when will I consider that I solved my problems? What do I want to know in classical mechanics? What I want to know is if I start with a particle at the point x, say, and time t, I want to know what particle is Rx2 after some time. It evolves with its speed, and so given the initial conditions, I want to know where will I end up, okay? So there is a very important tool that already contains half of the course, which is the concept of how do those classical particles move? And they move following a principle that is called principle of minimal action. So one of the things that I will collect here that will be important the action will be one of the most important tools that we're going to use. So the principle of minimal action in classical mechanics, what does it say? It says that a classical particle will move from x1 to x2 in such a way that it will minimize a functional, which is built with the particle. So there is an action, which is and the motion will be such that the path that the particle will follow will minimize the action. That's the main thing that I want you to remember from classical mechanics, because there is already everything that will be later in quantum field theory, the action and minimize. And it's even more than that. There is already a path, so particle will go in a path that minimizes the action. So in classical mechanics, we already find action and paths. Now, What do we get from this action in classical mechanics? From the action, we get the equations of motion, right? Just minimizing the action, you get the equations of motion. So exercise. Find them for a classical particle. Find the equations of motion from the action. Of course, you may say, well, come on. You didn't give me anything. You gave me an L. So here, the equation is, how do I build the action for a classical particle or whatever? For that, we need to use the symmetries of the system. We need to know not much more. So maybe this exercise should have two parts. One, find the action for this point particle. And B, derive the equations of motion, solve So we have, just in the first book of Landau, Mechanics, which is very thin, we get an action made, by the way, from a Lagrangian. So the Lagrangian is already there. It's nothing that we invented in quantum field theory. The Lagrangians are there. You go from Hamiltonian to Lagrangian in a trivial way. And also you go there in mechanics from x dot to the phase space, right? So you derive the momentum like the derivative of h with respect to q, and then you write things in terms of p and q, and there are commutation relations also, no? Paths and Euler-Lagrange. Equations. This is what we already get in classical mechanics. Any questions here? No, because it's classical mechanics. Now let's advance. This is an interesting exercise to just to remember when you were in the BA. The Landau book 2 is on classical field, right? So we were happy with our mechanics, and we could solve even, planetary motion and a lot of things in classical mechanics. I want you to think, and this is another exercise that I will ask you to do, to think what are the limits of classical mechanics. And later, since I'm going through all the subjects, I would like you to see what are the limits. So when I say what is the object of desire and what is the particle, what do I want to know when will it start to fail this description, and why. Why do I ask that? You all have seen this, but I want you to realize that all physical subjects, all the models, all the theories are effective. There is no theory of everything, everywhere, every time, right? So the idea that mechanics has a limit where it cannot be anymore applied is something that is important, but it will happen also in quantum mechanics, in classical field theory, and in quantum field theory. Nothing wrong. Why? Because what we want is to describe what we see. If we see more and we cannot describe it like that, then we'll invent more physics. But be aware that all theories are effective, are just valid in a circle of space or time or size or motion, right? Okay, so classical field theory. Why did we ever need fields? They were happy solving the planetary motion and everything. They needed fields because the electromagnetism appeared. Gravity was also there, classical gravity. So they saw that they were motion of things that could not be explained as two-body and body problem. So classical fields means that now you cannot stay with a particle at a point of space. Now you need the space filled up with something, with a field. So what are the two examples? Electromagnetism and gravity. Okay, even if classical. So what do we find in the Landau 2 book? Two very important things for later. One is from electromagnetism, we get the concept of gauge field. From gravity, we get, no, from gravity we don't get anything yet. From electromagnetism, we get the two main things, gauge fields and Lorentz group, or Lorentz transformations. Why? Well, gauge field, why? Because we have the Maxwell equations, and then we see that they are, well, first we see that the speed of light is the same in every inertial frame. I forgot to say that in classical mechanics, in the L1 that I already erased, there is a law for knowing if you are in here and some of your friends that is moving in a train there at constant speed, then how will you transform? So in classical mechanics, the law for transforming the things is just x prime equals to x plus vt, t prime equals t. Okay, and this is the Galileo that forms a Galileo group. This is, okay. Now, if there is some body, light, that when you measure its speed in any reference, in any inertial system, it is the same, then of course this thing does not work. So first 3 pages of Landau 2, they introduce the, I'll call it Lorentz, I don't know, I'll call it whatever. I want to make this precise. I don't know how. Well, this is amazing. This is amazing. I mean, I don't know how you get to it. Well, I know how to, but it is, there are two very important things here. Gamma, of course, is this relativistic factor 1 over square root 1 minus v over c. Square, square. This, as you know, encodes all the paradoxes of special relativity, like, time is not the same, the time interval will shorten, or so. So there are two things we see here very important is that time mixes with space. So time is no more a parameter that is wholly and will stay in all the systems and so on, but it means that if you're moving in an inertial reference system, the time you will see or your clock will be different, and that's very important. And another interesting thing is to see that if the velocity of your inertial system v is much smaller than c, then of course that goes to 1. So we already see how to take the non-relativistic limit. In any case, it's just take the factor gamma going to, or take v going, v over c going to 0, then you recover this Galileo, okay? But this transformation, this Lorentz transformation will play a very important role in quantum theory. So I just wanted you to have clear, see. I don't. Which, it doesn't matter. You take v, because, yeah, it's okay. V goes to minus v. Oh, I put that here. No, I don't want to put that here. Really doesn't matter. You recover. Make it so that you recover it. Okay? I don't know if I change this, I should change that too. It doesn't matter also. So the important thing, as I say, is that two messages. First, the time is messing up with space. And second, this wasn't invented in quantum field theory, this was invented in classical theory. Okay? So L2, we get Lorentz transformations and gauge fields. What are those? Those are you invent a gauge field, a mu, a gauge potential, a gauge connection or whatever, and then you see that the Maxwell equations written in terms of E and B can be much more nicely written in terms of this A mu. With this A mu, you construct an F mu nu. And then from there, you get that the Maxwell equations are just so exercise. Those are just reminders. So exercise that you, if you want really to have this clear, just to go to your books in class in BA and do this exercise. But the exercise I want you to make is get this as a Euler-Lagrange equation from the action okay? So you write down the action for the electromagnetic field and applying the Euler-Lagrange equations that were written there, or that I repeat them here. Then you derive the equations, the Maxwell equations, okay? There is another exercise, and again, these are things you have seen in the PA, but you may not have noticed, or as I say, you may not have paid attention to it in this way. There is another interesting thing that I would also, Lawrence, gauge fields. Gauge fields, I didn't get them yet. So, oops, sorry. What is, once you introduce this electromagnetic potential, what is a gauge transformation? If you move, you shift the electromagnetic potential with a total derivative of any function, then what you see is that the F mu nu is the same. So you get exactly the same electromagnetic tensor. So you get exactly the same electrodynamics. So this only tells you that there are redundant degrees of freedom in your theory. In the theory of these gauge fields, there are redundant degrees of freedom. And we know it. Why? Because, see, the point is that light being massless, I mean, a photon being massless has only two polarizations. And A mu, which is the field that will be the field of the photon later, has four polarizations. So this gauge freedom only tells you that you have too many degrees of freedom, and some of them can be eliminated. We will use that later in quantum field theory, okay? But for now, just keep in mind the fact that there is a transformation with a continuum parameter in this electromagnetism. Good, so what do we have here? We have in lambda 1 in action an Euler-Lagrange equations and Galileo transformation. In 2, we have Lorentz gauge fields, and also in action that allows you to get equations of motion, and then later I'll talk about these nether theorems that are so important and so on, okay? But I also want to see, to let you notice that this action, again, is like a sum over field configurations, yeah. Yeah, I'm talking about Landau 2, electromagnetism. It's not, it is a gauge theory, of course, a billion, U1. When you quantize and everything, that will be a billion, yeah. Then you can generalize it to non-abelian if you want to study SO3, SO3, SO2, blah, blah. But for now, I'm talking about Landau 2 book. Yeah, because non-abelian does not have much more physical content. It has more technical difficulties, right? But if you like non-abelian, we can discuss those. Not in the course, because you see, I erased what was my main aim, but my main aim at the end is to go back to Earth and see if I can understand what these condensed matter physicists measure. And they don't measure anything unabelian. Oh, well, okay, yeah, you may go to low dimensions and be unabelian. I will stay in 4, easy. And then I'll stay U1. But again, this is very interesting, maybe for a different course, the non-abelian aspect of it. Okay, there was another exercise that I wanted you to do here. Since you mentioned this non-abelian, first derive Maxwell equations and everything in 1 plus 1. This is a lot of fun. See how is the electromagnetic field, if there is a magnetic field or not, or what. And since you are here already, you can do it also in 2 plus 1. And see that the magnetic field is in fact a pseudoscalar and so on. So the electromagnetic field is only the nice electric and magnetic field that we know with like divergences and rotationals and so on in 4D. But it's very instructive to see how it works in these other dimensions. But this is a quite easy exercise, okay? Good. So, and now for something. So I'll continue a little bit with classical fields. Why? Because quantum field is just making the classical fields quantized. So quantum field theory is nothing but classical field theory after quantizing. So it is important to remember all you can from this second book of Landau or from wherever you studied electromagnetism, classical, and whatever gravity you studied, classical also. So let me give you examples of classical field, or let me give you the action of classical fields. You have the scalar field, and its action. I write them in a very complicated way, because that will be later used when I take this metric to be real metric in gravity depending on space-time. So this is Minkowski. So this is d mu square, the standard classical, no? Plus whatever. Then you may add interactions, okay? So the scalar field that you find in classical mechanics has this action. It is instructive to derive the Euler-Lagrange equation from this action. And there is another exercise I want you to do, which is the following. Take the action for a complex scalar field, okay? So psi d mu psi start d m, I don't care, and make a gauge transformation. So this field is complex, so you can make a gauge transformation, and derive, that's another theorem, okay. I don't like that, because I didn't tell you yet. So keep this exercise for 15 minutes later. I will ask you to do this exercise, but I leave it here because, so get the electric charge. The form of the electric charge later. After nether. Anyway, I think that I will already say nether here because then I will explore it further, but when did I start? Okay, good. So I should order myself, sorry. So the action. From the action you get also conservation laws, okay? This is again known, not nether. Is a theorem. I don't know if you notice that I say nether theorems, because this is the first nether theorem. There are more, because nether was a wonderful woman mathematician. But what we always see as a nether theorem is the first nether theorem that says that if the action of any system, now we already have the action for a classical particle in classical mechanics and from a quantum classical field, if the action of a system, that will be valid later for the action in quantum mechanics and in quantum field theory, is invariant under a continuum symmetry, then there will be a conserved current I'll write it in the simplest form. There are complications to that, but in the simplest form, there will be a current that is conserved, and it gives rise also to a conserved charge. So this current, it has something here that I will write when I discuss about the nether theorem more precisely, but by now, you just, for mechanics and classical field theory, you can stay with that. And then this will be conserved in the sense of that. And the zero component Q0 of this current is also conserved. It doesn't matter. So a continuous symmetry of an action gives rise to conserved currents and conserved charges. The typical exercise that I will not ask you to do because you have done it 1,000 times is prove that invariance under translations in classical mechanics implies conservation of the momentum, time translations is a conservation of energy, rotations, angular momentum. Okay, but this is more interesting because this is an internal transformation. So here, when you transform is the field, right? You do that. You don't touch space-time. And then it gives rise to a conserved current that will be very important all through this course, which is electric current, which you can derive it like that. But something that is also interesting is how is the electric charge seen as a function of the field. And so this exercise of take a complex scalar field and derive the charge, or first the current, derive the current from the Nether theorem is a very interesting exercise, straightforward, really, two lines. But what I want is just to keep the form of the current, of the electric current, because it's unusual. Okay, it's not Maxwell. It's a bit unusual, and the charge. Okay, but neither I will really insist on it much more later. So coming back, I'll make a wrapping up at the end because I know I'm being a bit chaotic. Sorry. So what I was doing here, and when this complex scalar field pop out, was to describe the classical fields that you already know and seeing their actions. So the scalar field is that one there with this action put in a fancy way, but it's just d mu square, d mu phi square. The Maxwell action, the vector field Maxwell, I already put the actions on where, okay. And there are no more fields in so far in lambda 1 and 2, scalar and vectors, right? When we go to quantum field theory, we'll see that there are extra fields, but tensors can also be there, of course. Tensors are just vectors with more indices, nothing important in the way they transform. But there will be spinors that you don't find neither in the lambda 1, 2, nor in the 3 that I am going to now. So let's go to L3. So what did we found in lambda 1 and 2? Mostly in 2. In 2, we found already relativistic mechanics, which is very interesting. So we already have unified space and time and built things that are covariant in the sense of with derivatives and so on. When you go to lambda 3, the quantum mechanics, the way we see it in the BA, or at least the way I saw it, it's like a bit going backwards, no? Because there you find what is the object, the main object there is the wave function that is defined at each point of the space, right? And what do we want to know? Similarly, as in classical mechanics, what we want is to know the transition from psi xt to psi x prime t prime, basically, right? But then we learned the Schrödinger equation, and this is an equation that says that, I don't know, derivative of E h dt of what? Psi. I don't know if I get correctly the i's and the h, but anyway, the Schrödinger equation has something very annoying since we have advanced so much in the first two books, which is here is time again as a starting person that will not mix with time, with space, right? So it's okay. That's the way it was. But that is, to me, step backwards in quantum mechanics. Of course, quantum mechanics is very interesting, and exercise find the limits of quantum mechanics, find to where will it apply, to what type of systems you can solve with quantum mechanics, and see when you have to abandon this thing. But in order to put quantum mechanics, to put them together with us, I will tell you what is the main thing that you may not have seen in the BA, but is very important. The path integral approach. Okay, so what Feynman wanted, in fact, he wanted to get rid of this time being different from space. That's originally in this formulation of the path integral. But at the end, what he ended up suggesting was something very weird also. Everything is weird in quantum mechanics, but okay. It's like, this is something that is amazing to drive on the times of Feynman when he did it. What it says is the object of desire was that, well, I now call it Q, but you can call it psi of xt and psi of whatever. Psi 1, psi 2 is all right. Yes, okay. So the quantum, this path integral approach to quantum mechanics, what it says is something very important, and it will be important later also, is that the wave function, when it evolves, it does not follow straight a path like in classical mechanics, like, okay, I'll go from here to there, and that's it, but that's my trajectory. I could have others, but the classical trajectory will be that one, okay? With these initial conditions and with this velocity, we will go from here to there through this path. Now, what this says is that in quantum mechanics, the wave function to evolve to go from one state to another, it will explore all the states around in this way. So that's a concise way to say that that the wave functions in quantum mechanics do wave around. Now, of course, what is very annoying is this measure is I'm integrating. So what does it say? It says that, okay, if you want to find the transition from an initial to a final quantum mechanical state, you have to sum over all the possible states that there will be in between, weighted with a measure, with a weight that depends on the action. Okay, so you see here h bar, you see here an I, which means that these phases will oscillate enormously if S is normal. Now, if S is really, well, say that the principle of minimal action here will say that the classical path is the path that minimizes this action, this S, okay? So here we find like the analog of the minimal action principle that we saw in classical mechanics, but in a quantum mechanic language. It's like, okay, you sum over all the trajectories, over all the possible waves, function or states of the system, and weight each of them with with a statistical weight. Well, phase is not a statistical weight, okay? But it will be very similar to statistical weight the minute I do a Weyl rotation. You want me to stop? Not yet? Oh, 1 minute. Okay, so important, the path integral approach to quantum mechanics returns the action to us and a path that, a preferable path for the action. Same as in classical mechanics and in classical field theory, okay? So the only thing that remains here a bit annoying for quantum mechanics is that it is not Lorentz invariant, so it's not relativistic. Okay, so we got rid of time as a specific, here with Feynman trick, we got rid of this preferable time. But we still know that it's the Galileo group what will rule the thing, okay? So we are almost there in quantum field theory, because now we have something, but not yet. So now I'll go to L5, just a minute, because this you know much better than I. I jump over L4, which is quantum field theory, is where I want to go. But I just remind you that in L5, in statistical mechanics, you have exactly the same kind of idea. So what do I want? I want thermal averages. I want correlation functions, right, in statistical mechanics. And how do I define them? I weight them with a Boltzmann factor, no? So, okay, I'll jump. That's what you have in statistical mechanics, and then this beta is 1 over k Boltzmann T, right? Now, this is very similar of what we found here, there, right? Only there was an I there that is not here, and there was H bar that is not here also. But there is something, I will go through it later, slower, but there is something that you can do here, is you do, in quantum mechanics, you do a so-called Wick rotation. So take the imaginary time and take it to tau, and then you see immediately that you get from quantum mechanical path integral to this, you get here. So statistical mechanics is quantum mechanics after Wick rotated. I will explore that more because I loved it. And this is one of the correspondences that I will make between lambda 1, 2, 3, 4, 5. I'll leave this 6, 7, 8, 9 for now. Okay, any question? Any remarks, desires? Okay, so a break. So welcome back. First, important, I'll notice a erratum in the previous place that will not allow you to derive the exercise that I asked you to do. So I remind you, I told you that just like that from the scratch, how the conserved current arise from the Nether theorem from the action. And I told you that, that the conserved current would be like that, and I missed this one. So of course, when you are dealing with the space-time transformation, maybe I shouldn't have started yet. No, no, clap. I repeat myself, doesn't matter. So welcome back again. I start by noting a erratum here. As I said to the people that were already here, what I did was very loudly just throwing on you the nether theorem first, and telling you that the continuum transformation of an action gives rise to a current that is conserved. And then I asked you to do an exercise, which was find the electric current corresponding to a scalar field, a complex scalar field. But in the rough current that I wrote down, I missed this term, which is very important. Why? Because you cannot get the exercise, you cannot do the exercise I asked you to do for the charge without this term. This term is all right to be out when there is a space-time transformation. Then this is the current for, translation, rotations, blah, blah. But if the transformation is internal, it happens that it is the gauge field what transforms. So this piece that I missed in the current is very important. Okay. In particular, for the exercise, phi would go to e to the I phi, alpha phi. So delta phi will be like I alpha phi. You develop that, 1 plus I alpha, and then you get the electric charge. Okay, so let's go now to Landau 4, which is our object of desire. Quantum field theory. Now, I'll ask again why, and this time I will not answer because it's fun. I answer because it's needed. Why? Because you observe that there are, particles decaying, there are radiative things, and the number of particles is not conserved. First, second, in the quantum field, in the quantum world, the particles, for instance, the photon, and also later in condensed matter, effective quasi-particles will move at speeds close to the speed of light, or even worse, they will be massless. So let me start with a digression. Why go to relativity? We used to say that when particles move at speeds near the speed of light, then you have to go to relativistic mechanics, and this is true. But there is something also that I want you to notice, is that what you do in classical mechanics, if for some reason you have a particle or a quasi-particle or something that you would treat as a particle, like these Landau quasi-particles, that has zero mass. Revise your equations in classical mechanics. Mass is there all the time, mostly down in the denominator. So you can say nothing about the massless particle in classical mechanics. You need to go relativistic. So relativity is not only because you move at high speed, it's also because there are massless particles, okay? And then you need the dispersion relation of Einstein, which is, whatever. Plus whatever. I don't remember. I'll write it later. Whatever. So Einstein allows you to describe particles that are massless, and they have energy because they move without any rest mass. So this is a digression. Now let me go to quantum field theory. The idea is, as usual, I need to describe relativistic fields, okay? And I need to describe a system where the number of particles is not conserved. So there are ways to go. So one main question is quantum mechanics, relativistic quantum mechanics, quantum field theory? And the answer is no. Relativistic quantum mechanics is not quantum field theory, because there, the number of particles will still be conserved. Second question, why? So this why, as I say, why, will not be answered as for fun, will be answered a bit more precise. Need to integrate relativity and quantum mechanics, okay? So quantum mechanics plus relativity is not quantum field theory. Why? Because the number of particles is not conserved, is conserved. Now, we have many body, which is Fock space, and there you can deal with non-conservation of the particles, or phonons. The number of particles are not conserved. You define the phonon as something with a precise momentum. Is many body quantum field theory? No. Why? Because it is non-relativistic, right? So we are almost there. I mean, we have one of the things that we know, but it's non-relativistic. So what the hell is quantum field theory? Its name, quantum field. Is quantum field theory, quantizing the classical field. There, you will see that when quantizing that the number of particles is not conserved, and you already are relativistic, okay? So relativistic quantum field is quantum field theory. Now, what do we have in quantum field theory? If you try to quantize the classical field, then what you find is that the field becomes an operator. So in quantum mechanics, what you have is a wave function, which is a function, operators like P, Q, or whatever, L, that act on the wave functions, and they are defined like they are not functions of space-time, they are just P or Q operators. Now in quantum field theory, the field will become an operator. When you quantize fields, then the field itself will be, in fact, an operator-valued distribution, but I don't want to mess with the words. The fields will be an operator, and the object of desire, say, so what we want is to get, I want to be more precise than before, because otherwise. Our object of desire is it's, oh. So, yeah, what is a classical problem in quantum field theory? Say that you have two electrons colliding and going out, and then you want the cross section for this process. Or you see a particle decaying into two particles, and you want the probability for this to occur. Or in general, what you want is to find, as in statistical mechanics and as in quantum mechanics, correlation functions. So what you want is to know what is the probability that if you start in the vacuum and let a field evolve with a certain action, the field will end up somewhere. And the way you do that is you, yeah, that's again path integral, but I'll come back to that. So let me go back to that. So in principle, what we have in quantum field theory, as same as before, is an action, which is a set of fields and derivatives of the field. Okay, this is the action that we, and then this is the, yeah, that's the Lagrangian, and now we'll build the action just as before. So we want something like a partition function. So we want to know what is the probability of a field to evolve into a certain way, no? And the main tool for this is to build a functional, which is called a generating function, which has two steps. First, you take the action and add a current. So you perturb the field with a certain current. Well, sorry. So this is the field, and this is it's like in linear response. So you perturb the action with something that is correlated to the field. And then you ask yourself, you want this thing, this correlating function that is called the generating function. So, and this is a definition that is very similar to this thing that happened in statistical mechanics when you go to the path integral, right? So what I'm trying is to avoid quantizing the classical field because this is boring. So what I am trying to go directly is what do we want? What are the observables of our theory and how do we get them, okay? And I do in a way that I will use later for my purpose, which is anomalies and all that. But the main, so the main object that our object of desire in quantum field theory is the generating function, because from there we get all the possible correlation functions. We get the propagator of a field expanding into H bar. We get in loop expansions, we get all the quantum corrections. So again, as usual, if you say that you want this phi x, phi y. This is ordered time order. This x, remember, is mu, so it has time also. Either time ordered or any order you want. This is something that would contain statistical physical the correlation length. And in quantum field theory, it is the propagator, which is something used in the Feynman graphs later to derive things. And this is something that you will find from here, just adding two sources to the action and deriving with respect to the action. This is something which is abstract, but I'll go later into that and how it works. So we get observables from that, from this correlation, from this generating function. And from this generating function, we can go to the effective function. Defining a classical field, that this is all, formal. It doesn't matter. Later, effective function. This is you do a Lagrange transformation to get rid of J, and then go to define classical field, and you define an effective function, which is classically is the classical action without interactions, and all its quantum corrections will give you all the possible processes in the quantum field theory. So the important thing, and I'm being very lousy here, I know, but I will be more precise later. Important is that the commutation relation of two fields the equivalent to the Poisson brackets in classical mechanics that I didn't talk about, but they are there, and of the commutation relations in quantum mechanics, P x equals to IH bar. The equivalent to that is the commutator of these fields that is proportional to delta x minus y, delta AB. Okay. And that's something that occurs simply when you quantize the classical field. That goes immediately like this. And this will be important later when you see the origin of the anomalies. But for now, I will just go from 1 to 3 to 4 to 6. So the summary of all this that I say is if you study quantum field theory, that I didn't at all, then you, of course, in the non-relativistic limit, you get quantum mechanics. In the limit in the classical limit, you get field theory. So say that from Landau 4, you get L3, you get L2. From here, you get non-quantized, H bar equals 0, you get L1, LR, the Landau books. And doing a big rotation here, you get also L5. So basically, if you learn quantum field theory and all these rules, which are really easy, just technical, then you are in a position to describe everything. And it is easy. So to deal with, so it's much better to have a photon from the beginning, a photon as a field, as a quantum field, vector field, than having to deal with the strange ways that the photons appear, for instance, in condensed matter, which is something strange. Second thing that I will see now is how spin is built in quantum field theory, which is not in classical in quantum mechanics. So I mention, because I don't want to seem like I don't like quantum mechanics. Well, I don't like quantum mechanics, never mind. But one problem of quantum mechanics, when you try to describe normal particles, is that a lot of particles are fermions. And fermions, if a spin half or 3/2 or whatever, a half, you just add a label to these fermions in quantum mechanics, and you invent a way of transforming them so that you will pick up a minus sign when you go around a circle. But this is very artificial. While in quantum field theory, fermions are proper particles just built in there with spin half. So I'll go now to fermions in quantum mechanics, in quantum field theory. So I know that there cannot be any questions here because I've been horribly lousy. So, but if you want to ask something at this stage, no, okay. So let's go to fermions because this is really, I mean, okay. So what do I want? Again, as I told you, this course will be how quantum anomalies generate new response functions on new transport that has been observed in some condensed matter systems. And as I say, the anomaly that we are going to talk about is an anomaly that arises when you have massless fermions, okay? So fermions. In quantum field theory. So I will tell you what the fermion is in quantum field theory, and also I will introduce you two types of fermions that play a role also in 1+1 and in physics today, which are these Weil fermions and Majorana fermions. Okay? So how do you build an action in quantum field theory or in any field theory? What you do is you see what are the symmetries of your problem and build something that is scalar under the symmetry transformation, okay? That's the way you do. So say particles in quantum field theory will have to be, there will be people that transform under the Lorentz group as a representation of the Lorentz group. I'll be more precise about that now. But the main guidance for building actions in quantum field theory is the Lorentz group. So I'll do a very fast view of the Lorentz group, and I will remind you what the representation is, and then I'll show you what the spinor representation of the Lorentz group is, which is what a fermion is. Okay, this is the boring, I mean, that will be the technical part of this first session. Later I'll be more ordered, I promise. But this technical part I think is important to have it clear. You don't need to reproduce everything, but to have the set of ideas, the line of ideas clear. So they have to, so particles, acceptable particles in quantum field theory have to transform according to representations, or better, irreducible representations of the Lorentz group. So I'll tell you what the Lorentz group is. The Lorentz group, yes. Yeah, what a pity. No, sorry. Yeah, so. So you don't need the quantum field theory? That's what you mean? But it's much better if you know what Lorentz is and then you break it. You know the rules and you break them, and then you go in the right path. What you cannot do is breaking the rules that you don't know. So I'm trying to tell you what are invariants of the Lorentz group, and then you will be able to break it in a good way so that you will not spoil everything, right? So, or is there anything else in your question? Because maybe give me an example. Okay. You can run into a lot of troubles. Causality, locality, many troubles. So, but I think that the best answer is know the rules and break them, because then you will break them in a sensible way. So if you want to go non-Lorentz invariant, you better know what Lorentz is. And then you decide to break this little piece or this other one that will not spoil the whole thing, okay? I mean, okay, if you can do whatever you want if it describes your system, but it's much more efficient if you do universal things that describe everything. And now you break here and there. I'll break Lorentz later. I've been living out of breaking Lorentz, but you break Lorentz as I say, in a sensible way. So first, since we wanted relativistic fields, first our fields have to transform correctly under the Lorentz group. That ensures relativistic. Plus, we want locality. Locality means that you cannot act at the distance. You cannot move a field here and instantaneously see what reaction there. This is also a part of relativistic things. So locality means that all the actions will be built out of fields and derivatives at the same point, okay? You will not have ever an interaction like psi x, psi y over x minus y or square or whatever. Because this is non-local, and non-local is non-causal. Means that the things can happen before you act on them. And we don't like that. So quantum field theory has to be built, an action in quantum field theory has to be a good invariant under the Lorentz group, has to be local, which ensures kind of causality, and well, fields have to have some properties of analyticity, but this is that will be important if you want to Wick rotate something, then you better don't have singularities in this part of the plane where you rotate, but this will not play a role in this course. So, for instance, say that you want to quantize the scalar field, it is already done. So, half or quarter or whatever d mu phi square and then you interact, well, m squared phi squared plus interactions that are polynomials in phi and derivatives. This action is already, this Lagrangian density is already a Lorentz invariant if the field transforms as the scalar representation of the Lorentz group. And of course, the other one, the f mu nu square, a fourth nu, is also a Lorentz invariant because you can see that the a mu scales as the vector representation. I tell you now what it is of the Lorentz group, and this is a good tensor, and contracted those two good tensors, you get a good scalar. So the fields that we are already know, and they're very useful because in particle physics there are no scalar fields. Maybe the Higgs is, but it's anyway. Fields are always either fermions or vectors, right? So, but the scalar field is very interesting for statistical physics and for everything. And Maxwell is our main guy, apart from fermions that I didn't introduce yet. So let me go first to the Lorentz group. So our aim is to construct actions for the quantum field theory, and our tool will be Lorentz invariant. For that, we need to know how people transform so that you can build multiplying people that transform correctly, find scalars, right? So what is the Lorentz group? It's a group of space-time transformations that leave invariant the interval. Right? Why is that so? Because, you know, if a particle travels at the speed of light, then for a dt, you have a dx squared equals to c squared dt squared. And then you want this to be invariant, so this different has to be invariant. Or this metric which is a standard Minkowski, is invariant under the group transformation. So you want transformations of space-time such that leave invariant this thing. And then you are sure that whatever you build will be Lorentz invariant. Okay? So what are the transformations that leave invariant this interval? They are basically in 4 dimensions. The Lorentz group is SO 1, 3. And as I was telling to some of you, the meaning of that is special, meaning determinant 1, orthogonal matrices, and this means that you have one space and 3 time things. It could, and so it gives something called signature of the metric, but it's just the one is just that you have one space, one time like variable and 3 spaces. The Lorentz group is it's not complicated, but has components and is orthogonal and I don't know what. I will stay with the main Lorentz group, which is essentially it is rotations in SO3 and boosts, which are these transformations of X prime, it goes to gamma, and so on. What I wrote before is called a boost transformation, where the one reference frame moves with a constant velocity with respect to the other. So now, how many components have these rotations or have this thing? Rotations, there are 3, right? And boost, there are also 3. You can boost your system in 3 directions of space. So in total, you have 6 generators of the Lorentz, or 6 generators. Now, these transformations that are the Lorentz transformations, since this space I'm doing it in d equals 4, I will ask you later as an exercise to do it in d equals 2. This lambda will be 4 by 4 matrices, right? So far? Okay. So what is a representation of a group? Definition: a representation of a group is a set of matrices of any dimension that obey the group relations. Mm-hmm. So fields will transform as. This is the transformation that you will do. This is the representation that you're choosing, a set of certain matrices, and the field will transform like the group relations is only that you have an inverse, you can compose 2 elements and get another one. Is standard group like the sum in arithmetic, okay? Now, what are the generators of a group? Those, I didn't mention that the Lorentz group is a Lie group, meaning that it is, you can exponentiate it's like rotations, you can build up generators, infinitesimal generators, like e to the I, j, and then you generate rotation. So Lorentz group is the same. And so if you describe an infinitesimal transformation that live in the Lie algebra of the group like that, these are the parameters, and these are the generators. Okay? I'll give you an example. You want to describe rotations, 3 generators. That's an example you know from quantum mechanics and from everywhere, everything. This is the SO3 group. So you can write the rotation of an angle theta as e to the minus I theta and j. And those are the generators. In particular, imagine that you want to rotate delta theta around the z-axis. Then what you have is equal to I plus delta theta x, and c, which is the axis, stays. And this, you can write it as x prime equal to x plus delta theta. Okay, I threw them all. This will be the j corresponding to a rotation on the z-axis of an angle delta theta. I will use that later to show that fermions, when they rotate, pick up a sign minus. So maybe what you are used to see for the rotations are in the vector representation. They are like different, like 0 minus I 0. This is what you are familiar with the standard Pauli matrices, right? Obviously, these J's satisfy these commutation relations of the rotations. And that's it. Okay. Now, the Lorentz generators are a set of antisymmetric matrices, antisymmetric, that obey the following. But so far, it's just to say that they are elements of the Lie group. They you exponentiate and you get infinitesimal transformation. But what is important is that these generators will satisfy the algebra. Mu rho sigma. This is a bit long, but it's all right. Mu rho nu sigma. Okay. I need that to define the spinor representation. I'm sorry, because otherwise we'll be lost as before. So m nu sigma minus zeta mu sigma m rho minus mu rho sigma plus nu sigma m mu rho. Okay. Now, so the representations that we already know are like the scalar represent. Yes. With this, with the indices. Okay, I need here mu rho nu sigma nu rho mu nu rho mu sigma. Here. Mu rho mu sigma. Okay. Yeah. Now what? Nu rho mu sigma. What's wrong? It doesn't matter. You fix it so that all the that all the indices are correct. But tell me again what's wrong now. That's too bad. So you have to permute all of those. Maybe I got it right here. Nu sigma mu rho. Sorry. Is that okay now? Okay. These things is better to really work them out. It's absurd to do it in the blackboard, but I need it. Now we go to the spinor representation. Go in yellow. So there are few ways you can introduce this spin. Sorry. Maybe I leave it then for the next class. I wanted to finish with this boring part, but a couple of minutes. I'll do my best. Yeah. But I won't get to the Weil spinors or Majorana for sure. Okay. So, so there is a way to introduce this. When Dirac wanted the linear equation that treated the time and space on the same foot and would be quantum and describing fields, he found out that you cannot like square root the Laplace, the Lambertian to get something sensible. You cannot make this linear thing so that when you square, you get the standard D'Alembertian. You cannot do it in the space of real or complex numbers. You can do it in the space of Grassmann variables, and you can do it at the price of introducing matrices in your action. But if you just blindly want to continue with this, oh, let's build representations in any dimensions or any kind of matrices, then there is something that is interesting, is the following. Let me define what a Clifford algebra is. This is simple. It's just a set of matrices such that this is a Clifford algebra. And mu, nu are 0, 1, 2, 3. Later, we can go to 1 plus 1. Now, you can show, or you can take as a fact of life that the quantity, this one, forms a representation of the Lorentz algebra. So these matrices, as mu nu, define the spinor representation of the Lorentz group. Okay, so this is the important thing. You just take these two definitions, and you see that those are generators of the Lorentz group. This is mu nu. Next day, I will develop this a little bit more, and we'll see how the rotations look like in this representation and how. But this is important because this is what defines spinor. So if you decide, these people are matrices for 4x4, so they have indices. Say, put index in the matrices. Indices. S mu nu alpha beta. Then spinor field is somebody that transforms in the Lorentz group of this matter of the following way. So you do a lambda Lorentz transformation, rotation or boost or whatever, not much more than that. And then the spinor field will transform according to this rule. What is interesting is that it looks very much like the vectors, no? Because this, one index and so on, but the spinor is not a vector. is not, this index is not a vector in this index, it's a spinorial index. And we will dive more later in what spinors are. But this is the definition of what is the Lorentz group, what is the spinor representation, and how a spinor transforms. So in the next session, I will dive onto this. Any question? Are you too hungry? Yes. Again, yeah, I'm so sorry. Alpha, beta. Well, this was also a typo. Yep. Here, here, there should be what? Yes. You want the square? So this is, so, okay, this I defined. It's gamma mu d nu minus gamma mu d mu. That's what you mean? You're right, completely. Okay. Any more questions or typos? So thank you very much.